Thank you for the warm welcome. Hi everyone, my name is Neville Dipale. I'll be talking about gracefully oxidizing a web application into Rust. Okay, about me, as I've just mentioned, I'm Neville Dipale. I came all the way from South Africa with my girlfriend there. I'm an accountant by profession, which is a bit weird when I mention that, because then people ask me, how did you move from accounting to Rust? So I currently work as a data engineer, mostly do independent contracting. I spend a lot of time at Deloitte in South Africa, where I'm part of the data analytics team. I've been programming as a hobby. Started off about 12 years ago with PHP and JavaScript. I've gone through Python, SAS, SQL, a whole lot of stuff until I eventually got to Rust. I run a public transit information service. So if you go on Google Maps, something that you take for granted when you, let's say in Italy, you open Google Maps and you're saying I want to get somewhere, and Google Maps shows you all the public transit options. So in South Africa, I run this with a friend of mine as a hobby, where we provided people with the same kind of information. I started using Rust about 12 months ago, and for me it was also a choice between Go versus Rust. I chose Rust because partly because every time it was on Hacker News, there'd be, I guess, all this excitement about the language. I recently became an Apache error committer, so I'm working on the Rust implementation. So Lucas talked yesterday about data frames, etc. I'm part of that initiative, trying to see whether we can get data frames. I'm working in Rust. Okay, so about my talk, I'm going to be talking about our experience using Rust in production, using in our hobby / pet project, whatever. I'll be talking about how we ported some web services to Rust, the oxidizing bit of it. And I'll talk about how we managed to replace critical services or endpoints with Rust with little disruption to our users. So that's the graceful bit about it. And then I'll share our approach, the challenges that we came across, as well as our benefits. Okay, so what do we do? I've mentioned that we effectively source public transport feeds. Sometimes it's as primitive as we get on the bus with a phone or a GPS tracker. We look at the route that the bus takes, where it stops, what time it stops at those stops, etc. We collect all of this information, and then we make it available to people in the public. We've got about 1,200 routes, so this covers a good part of our province, which is quite big. There's about 10,000 trips a day that are made by vehicles in our data. We currently crowdsource live information, so which people can subscribe to after. So we're sort of creating a Waze for public transport. The idea is, if I get on the bus at the first stop or at the departure, and I open my phone and I say, okay, I want to share the bus route with other people. People along the route who are waiting for the bus can get real-time updates on when the bus is arriving, because generally we've got very old, well, not very old, but some of our buses are quite old, and they don't have GPSs fitted into them, and we don't really have a very efficient government. So even if you propose, okay, let's put GPSs on the buses and give people real-time information, it takes forever, and then sometimes it doesn't happen. So we resorted to crowdsourcing the information. Okay, so the problem that we had was with our own vehicle streams. Okay, I had to crop my presentation from the bottom, but I didn't see that the top is quite high up also. A lesson for the future. We take schedules and live feeds, and then we calculate transit movements. There's about 700 trips running at peak time. So peak time would be in the morning when people are going to work, and then in the afternoon when they're coming back from work. Our feeds are updated every 7 seconds. So if you look at a bus feed, every 7 seconds we sort of give you an update of where the bus is. Feeds are consumed by the website, our app, and then we've got various subscription services. Like we've got an SMS service where you can via USSD or SMS say, well, send me a text message on the buses when the 8 o'clock bus is 5 minutes away from my nearest stop or my house. So this was very unstable in JavaScript. We ported it to the JVM, and then we just kept throwing RAM at it. I'm sure this would be a common experience with a lot of people. So how do vehicle streams work? We poll MongoDB. We've been using MongoDB forever, so it kind of hurts me sometimes when I see a Hacker News article and people are bashing it, because I think we've shown that you can actually use MongoDB for a lot of things other than dumping logs to it and analytics, etc. We use it quite extensively for geospatial features, and as a result, I've been quite not involved per se, but I've spoken to a lot of the former and current MongoDB engineers around geospatial stuff when we've got feature requests or using the aggregation framework trying to figure something out, etc. So the process works like this. We determine if a trip is live. So a trip is live if somebody is actively sharing their trip information with us, or where we're lucky if the bus agency gives us raw access to their bus feeds, or otherwise it's estimated. If a trip is live, we project. I don't really want to call it an algorithm per se, because it's all linear and quite simple right now. So we just project the movement, the speed and direction of the trip, and then we project when it's going to get to a stop. We estimate how long it normally stops at a bus stop. Is it 15 seconds or 10 seconds at peak, off peak, etc. And then we just project the rest of the trip for everybody else. If the trip is not live, that's easier because you're just going to take the schedule as the trip is scheduled and then just apply that linearly. So here at the bottom, you can see a bus. The color wasn't great. I was trying to make it more visible. You can see a bus on a route. The green and the red are the departure and the destination, and then the amber ones or the orange ones are the stops that the bus makes throughout. Let me just show you a quick example, because I'm going to do a bit of a demo with it later. Okay, so here's one where you've got a train. It's going through a long distance. This is around Johannesburg. So if you watch it every 7 seconds or so, you'll see the train icon moving, and this is what vehicle streams is about. Okay, so our tech stack, quite simple. We run a website and an Android app. Website is powered by Node.js and Express, something I hope to move away from at some point. Well, maybe to Rust. Vehicle streams, we moved them from Node.js to JVM. This was around the time when Kotlin reached 1.0, and because of the Android movement, we started using it. I hated Java before that. Every time I had to use it at work. Yeah. So we've also got a trip subscription manager, which is mostly still in JVM. And then we've got other relevant services. Okay, so why the JVM? As I've mentioned, I don't really like the JVM. But I appreciate its strengths, and some of its strengths being stability, the ecosystem around it, etc. We needed this stability because an uncaught error, especially in a giant Node.js application, somebody else would be maybe sharing their trip, their live locations with us. Somebody's browsing the website, and then here's a random error that just brings everything down because it's all one application. And then you spend 2 seconds restarting it. So that's what we were trying to move away from, and it was a natural choice then to say, okay, well, let's move some of the critical stuff away from Node.js to the JVM and run it as a separate service. So the JVM promised a stable application, which it gave us, and Kotlin felt very close to JavaScript and TypeScript. It's also at the same time when I was learning TypeScript. So you can see there's always like a lot of learning languages, especially at the same time. The experience deploying Java applications was worth it, and I'm talking about this more from my professional career perspective. Being in data engineering, a lot of the data engineering stacks or tools are in Java, and having the experience of being able to run and manage an application lifecycle in Java, and not talking about Wildfly, JBoss, etc., but just knowing what's happening was quite well worth it for my career. Okay, so the Rust appeal. Vehicle streams was running slower with more routes being added. We currently have around 1,200, as I mentioned. By the time that we started working on vehicle streams, we were, I think, at about 800 routes. So the more routes we added, the slower it was starting to become. We had to restart it at least twice a week to reclaim to reclaim our memory. Actually, we moved from using a server with 12. Everything is self-hosted. We just rent some server somewhere in Nevada in the US. We moved from a 12 gig server to a 64 gig RAM server, mainly because of vehicle streams. So it was becoming a very expensive hobby. I mean, I used to pay like $200 US to, I think now I pay like $1,300 US. But by contrast, my vehicle installment is twice the amount. So I'm spending half a car every month just sustaining this thing. C++ was the next frontier of performance and hopefully stability. But it's still intimidating. One of the things I'm doing part-time is studying, and one of my modules is C++. Theoretically, I should ace it, but I'm repeating it for the second time because I just find C++ so intimidating that I don't give it enough time. And you know, the problem with you could be a good programmer, but the problem with doing, especially computing 101 or statistics 101, etc., is that the lecturer will want you to do things in a certain convention, and sometimes you use to your own convention, which might be better than what the course material says because it's from 1990 something and it hasn't been updated. So I'm dealing with just those troubles, but I'll ace it this time around. So Rust appealed to me as a C++ equivalent that felt closer to TypeScript, because now I've got TypeScript. I sort of get the type stuff, especially when you started programming using the likes of PHP, JavaScript, Python. Types become quite foreign to you. And moving from, let's say, JavaScript to Java, where everything must have a type, it makes it very difficult, and you sort of feel this burden of having to, put types everywhere. So TypeScript being in the middle of thou shalt have types, and we don't really care, was quite great. And I found Rust to be like that. But okay, so I don't need to follow the 11th commandment of thou shalt have a type. I can just sort of wing it and see what happens. So it felt closer to that, and it became quite easy for me to adopt it and try it out. Okay, so I think 2-3 months after, actually no, about a month or so after I had learned how to use Rust, it was now time to put it to the test. And the best way to learn a language, especially a lot of its features, is to start trying to implement the language or implement something in the language. And what better way to implement, or what better thing to implement than something you've written before? Because then you don't have to worry about the overhead of trying to figure out how to do things, because you know how things should work. And it's normally just a direct translation from one language to the other. So I did that. I took a smaller service that we had written in Kotlin and converted it to Rust. The service's name is called geofency. I'll explain what that is now, but how many in the room have used an application called Tal38 or heard of it? Tal38, okay, cool. So Tal38 is a small in-memory database. It's a geospatial database, I guess, that implements the Redis protocol. It's written in Go, and what it allows you to do is to set up geofences as well as to index locations. So let's say, for example, you've got an app with 10 of your friends, and you want to know whenever any combination of two friends are within the same, maybe in the same building, for example. You'd set up a geofence around the building, and whenever you both enter or one of you enters, it'll ping a notification to say, well, you've entered the building. So this becomes relevant for us in saying, okay, well, you want to know when the bus is 5 minutes away, so let's set a geofence around the perimeter we expect the bus to be at. When it's 5 minutes away, we get a notification, we send it to you. Simple as that. Geofency has 5 functions that we had to map from gRPC to Redis. And here's an example of our protobuf package. We've got a service here, and here are the 5 functions. So we've been using gRPC since, I think, version 1.0, which was released around either March of 2016 or September 2016. So a lot of the services in our backend are quite, well, actually they just use gRPC. So here's an example then of one of the functions being ported directly from Kotlin to Rust. And it feels a bit, well, there's slightly more lines in Rust, but it's a function of the Redis library that we're using. In this case, we've already had a lot of boilerplate setting up the variable called sync, which is the asynchronous interface into the Redis library, whereas there we have to do a bit of connecting, unwrapping, etc. So you can sort of see that it looks like a one-to-one translation mostly, and that's what we did for these 5 functions. And then after that, we ran them in production. I looked at htop. I looked at the geofency in Kotlin, geofency in Rust, and this was the difference. I was using 97% less RAM, so I went from about 240 to 8 megabytes of RAM at peak time, and there's still room for improvement, because at this time, actually, during the time that I wrote all of these things, I was still a beginner. I was cloning everywhere, because when in doubt, you clone, right? Yeah. Okay. So then I grew bolder. And then I decided, okay, well, it's time to port vehicle streams because this thing was using about 20 gigs of RAM at peak, and that's why we have to keep on restarting it. So obviously I might have done something wrong, created memory leaks in Java, but I think I know the culprit, and I'll talk about it as you go along. So it's part of another gRPC service which has 36 endpoints. Most of them are handled by Node. Okay, someone might say 36 endpoints, that's quite a lot, but they're all very closely related, so I didn't want to break them further into separate services. Vehicle Streams version 1 handled 8 endpoints. All of them were streaming RPCs, and this is the kind of thing that they powered. I just want to show it quickly. Let me just refresh this page. Oh, okay, cool. Done it. Have to fly down to home from Italy. I think the first time I loaded it, it was still in South Africa, but now, okay. So you can see the 77 vehicles running. This is just a nice visual way of showing what vehicle streams does. And there's one vehicle there. Here's a cluster of them. All of these are all generated every 7 seconds. Okay, it's still loading, but you can see it's just buses and trains on the map moving in whatever random direction they're moving in. Okay, so we decided to take the same approach as GFNC, port endpoint by endpoint. Initially, it was a lot of effort, and it required rewriting a lot of functions from a lot of existing libraries, because one of the disadvantages at the time, and maybe even still now with Rust, is that you don't have the same rich ecosystem as you have with other languages. Okay, so there's a sample of those streaming endpoints there. One of them is, for example, submit vehicle position. It's a bidirectional streaming endpoint for those who are fluent with gRPC. And what it allowed us to do was a user with the app would just constantly send a vehicle location, which is just GPS, speed, direction, and accuracy. And then we just return trip updates. So if you're on the bus looking at the route that you're taking, you keep sending us a stream of updates, and then we keep periodically just telling you how far, well, giving you an ETA based on how you're moving. Okay, so we had a lot of porting challenges. I'll talk about them now. The first one, as I briefly mentioned earlier, was the language and ecosystem. So we needed geospatial functions and RX Java equivalents. So those are the two main things that we needed. We had to port a lot of functions from turf.js, because I think if you look at turf and you look at other geospatial libraries, especially the older ones like, I forgot the name, but it's used by quite a lot of programs, including PostgreSQL. You'd see that turf.js is more beginner friendly because it's written in just simple functions in JavaScript, so you can easily port it between languages. We rewrote a lot of that because, for example, if you look at the function that calculates a distance of a line, its immediate dependency is a function that calculates a distance of 2 points, and that has other dependencies, etc. So we had to just keep on going through and say, okay, well, this function now needs that one, let me rewrite it, etc. And then expressing some concepts in Rust was very hard for a beginner, especially when you're going to the very helpful community and you're saying, hey guys, I'm struggling with doing this, how can I do it? And then somebody tells you, well, use a generic or use this or that. At that point, you're a beginner. You just know you just know what you've learned, and it becomes very difficult to express a lot of concepts. So most of the times, we end up just porting things like for like, even though there might be some optimizations that you could do in Rust, which makes our code a bit verbose. Also, there was a lack of good gRPC crates at the time, so it meant a lot of experimenting. We had gRPC by PingCap, and then Tower gRPC still had that giant disclaimer saying, do not use this in production or else you'll regret it, blah, blah, blah. So as I mentioned, this created verbose code, so it took about 4 months to port this. I did it in my spare time after work and on weekends, because this is effectively a pet project. Okay, streaming was another one that was interesting. So having spent months being invested in the RX ecosystem, RxJS, RxJava, etc., and then coming to the streaming model of Rust made it quite difficult. So Rust pushes data, and RxJava pushes data, and Rust polls data, and that makes it difficult to express some things. So let's look at an example here. You've got 3 consumers that are interested in a vehicle stream. There's no filter criteria specified, so it looks like that page that I just showed now. Just let me connect to the stream and just give me everything. I'm interested in everything. And then the publisher just keeps sending data. The consumers must handle back pressure, etc. So here we've got a vehicle stream publisher that just keeps sending data to consumers. And then if you add a filter in, it's the same thing, except that each consumer says, well, okay, I'm only interested in the line that's going, let's say, to Rome. Another one says, I'm only interested in vehicles between 6 a.m. and 8 a.m. And then the other one just says, I'm only interested in buses and not trains or whatever. So the filters are quite expressive, but that's irrelevant for now. It's just that there's a filter that's coming in, and there's so we'd put a filter in between. In RxJava terms, that would be, we'd create a publisher. There'd be a subject there that consumes from the publisher and also acts as a publisher of its own. And then the logic to I guess, filter would be handled by the filter. If you express that in Rust terms, you've got the same kind of example, except now you've got consumers that are polling the vehicle stream to get data. So once I poll the stream and get data and use it for whatever I need to, I'll poll it again. So that's where the benefit of handling back pressure comes from, because the consumers can determine the pace at which they want to get their data. So the difficulty here is that in this instance we've got a single producer, multiple consumers, and that's not supported, at least last I checked, in the standard futures core, because you've got in the futures crate, because you normally have multiple producers, single consumer. There's cross beams and other crates that help with dealing with this, but again, I was a beginner at the time and it was very difficult to get things working. Similarly, if you do the filter, this is where actually I gave up, because I had a stream, I created a filter. The first consumer, the filter worked. The first consumer started getting data, and then I sent the second consumer. The second consumer didn't get any data, only to realize that the problem was that the first consumer actually owned the stream somehow, because I couldn't clone the stream. I think this might have been solved since I was using Tower gRPC at the time, and if I gave a stream to a consumer, the other consumer that came would just get nothing. So that was quite a problem, because I couldn't scale the application. I would only have one person connecting and getting a stream, and then the other 999 get nothing. And the other problem was that once the consumer goes away, the stream just kept on continuing, because there wasn't a way for the consumer to come back and tell the stream that, oh, by the way, I'm no longer interested in data, because the push method actually handles that, because the next time you try to push to something and you realize that the connection is closed, you can then unsubscribe from the stream. Okay, so as mentioned, I found translating that RxJava concept to Rust to be quite difficult. As mentioned, there might be crates that do it. Streaming, the other thing was if streaming without any consumers. So I'll start a stream and not have any consumers, and I'd get the typical, what is that error? Futures must be, oh yeah, what is it? Oh, futures do nothing unless polled, or streams do nothing unless polled, because we have to keep on polling from the stream. And then Carl said, okay, I talked about cancelling a stream, etc. So what I ended up doing here was that I created a sink, if I can call it that, or my filter became an external application in this instance. I used nets.io, which is a nice replacement for Kafka if you're not using advanced Kafka things like Kafka SQL, etc. This is yet another thing that ends up helping you save a lot of RAM, because Kafka is also quite RAM heavy, being part of the JVM. So we created a single subscriber as nets that would connect to the vehicle stream and just keep on consuming the stream. And then it would create some back pressure for us with our consumers and also act as a filter. One of the benefits with nets was that its syntax is quite nice, because you can actually, as part of just the syntax or the filter criteria, specify what you need. And it was quite expressive enough to allow us to handle most of the filtering there and still handle some in the stream. So effectively then we brought back Node.js to handle this. One of the benefits of Node.js is being that it's quite good with WebSockets. The page that I showed here, actually, yeah, the page that I showed here just pulls data through WebSockets. Okay, so this ended up not being replace all the streaming endpoints with from Java with Rust, but we ended up just taking the more expensive calculations and just porting them to Rust. So persisting vehicle output is very expensive because it generates about 10 gigs of data a day. The thing is, if you're interested in a vehicle update at 6:15 and 24 seconds, you'll only be interested in it at that time. So saving it to disk was just useless because you keep recalculating this stuff every 7 seconds. So the problem here was that the trip update endpoint, the one which shows us this guy here, the single trip. Oh, trip has ended. Let's just find another one quickly. Okay. Okay. I just wanted to load it because I'm going to use it again later. The thing that allows us to do that tends to take about 2 seconds running. In the backend, there's a complex MongoDB aggregation. I've optimized it as much as I can. That takes most of the time. And then the rest is just Rust calculating the update. Is it on time? Is it delayed, etc., based on live or estimated information. So the solution here was to cache calculations from vehicle stream and get updates from the cache. In version 1, we used the Apache Ignite. It's one of the, I think they call it an in-memory computing grid. So there's quite a lot of cool stuff you can do with Apache Ignite, but sometimes it becomes overkill if you're not running in a big data distributed environment, because it's really meant to be a distributed cache. It's meant to be a in-memory SQL engine and all sorts of things. So here's the endpoint that I was talking about. You send info of the trip that you want, and then you get a trip update back. Okay, so the next challenge here is now finding a thread-safe in-process cache in Rust. So moving to vehicle streams in Rust meant finding a replacement, because even though I moved from Java to Rust, the 2 seconds was still it was untouched effectively because a lot of it was still going back to the database. We ideally needed a TTL cache, a time to live cache, that would handle serializing or deserializing bytes from me. If you use Redis understands bytes, so you have to serialize your data structure into bytes, send it to Redis, deserialize from bytes when you get it back from Redis. So we wanted something that would do that for us, because Apache Ignite would just persist or cache Java objects. And then the other thing was Apache Ignite was in process, so we didn't really want to hit the network in going to our cache. So we ended up with looked for a hash map with a time to live effectively, and then went to crates, found one TTL cache. I think I struggled a bit with using it. We had to open a few issues and get them resolved on getting the cache working, but then eventually it worked. So now it works, but I'm running on a single thread. So now I wanted to be able to share the cache among threads and be able to write to the cache, read from the cache, because I needed a dedicated thread that just keeps updating the cache, and then I needed to be able to read from the cache every time that a query came by. I went online and I searched how to do it. I came across Arc and read write lock. I just followed the documentation, and Rust just made it delightful. So I ended up creating some state in my gRPC service. So I've got a client, which is a MongoDB connection. It's also effectively an atomic ref counted cell with a client inner inside. So it meant that I can also copy it among threads. And then I created my cache here with the TTL cache of a string and a Bison document. So in implementing this, the first thing I had to do was in the current thread, I had to create a one-shot channel, a future channel, clone the cache in MongoDB client. You can see it there. So I'm creating the sender and the receiver, and then I'm cloning my client and my cache. In my next step, then I move the cloned caches, or I move the cloned objects into a new thread. I tried to read from the cache. So this is where the read-write log comes in. And you can see I was using unwrap a lot because I hadn't figured out how Rust errors work. And this was, I think, the question mark was still nightly. So the other alternative was to use the try macro. It just felt too complicated, so I just unwrapped everywhere. Well, it's still running, so at least I'm having had errors in this case. So then we try to get the document from the cache. If we find the document, then the next step is we calculate the update for the document to create the trip update. And then once we're done with the trip update, we send the trip update back to the one-shot channel so that we send it out of this thread into the main thread. And then in the main thread, we just clone the cache again. We get a handle to the cache, a writable handle, and then we just insert the cache. So I wrote this, and in a space of about 30 minutes, writing it and reading the docs, I ran my application, and it worked. So this was quite great for me, because if you were to look at the equivalent in C++, it would be very difficult, and the amount of warnings that come after that are quite a lot. So this was really pleasant for me, and I think I gave myself a pat on the back at the time. Okay, so the result was a painless in-process thread-safe cache, and that was awesome. Now, when coming to testing and production, so we ran somebody asked me about load balancing earlier. So one of the things of being a cowboy running services as a hobby is that you tend to not implement all the fancy things like Prometheuses and Grafanas and whatever. Everything is just very simple. HTOP is my monitor. I log to console. Sorry, I log to console and pipe to file. And my proxy, because of when I adopted gRPC in 2016, Nginx didn't have gRPC support. Actually, nothing had gRPC support at the time. I think, what's that thing? Lyft Envoy had just been announced or got announced a few months later. So there was this service called ng-http2 or ng-httpx. It had a lot of arcane, well, I guess dark magic in terms of compiling it. You have to compile it yourself at the time and then get it to run and all of that. So I used that for load balancing. So what we did here when going into production with this new streaming endpoint effectively is I ran the Rust and the JVM version side by side. So you can see here, this is the ng-httpx config. You've got your backend, you've got your host, your pod, and then the endpoint, and then your protocol. So we've got vehicle streams, JVM, and the pod. I think this was running on a container. Redacted, that's a service. And then get trip update. So that's the full endpoint and then protocol. So if you specify the same endpoint, ng-http2 will just do very simple round-robin load balancing. So this is how we did it. And then here's other stuff that was going to Node.js. So we did it this way, and then just started testing it among a few people. We picked up issues, and the issues are that the vehicles would time travel. So typically the vehicle will keep moving forward. Every 7 seconds you'll get an update of where the vehicle is, but once in a while it would sort of jump back and then start moving again. And that was when load balancing between the JVM and the Rust application. So went back to the drawing board, looked at it, and it was a function of if you've done distance calculations with the harvesting formula, you'll know that some libraries use 6731 point whatever kilometers as the Earth's radius, others use a different one. So it was a function of that, and it was just hidden somewhere in the detail. So we fixed that, and then everything was working. No more time travel. And then after a few days of balancing both, we switched off the JVM version by just commenting it out and then restarting the service. Simple as that. No fire alarms in prod, and then about a week later, fire department checks up on me. Still nothing, because we didn't have to restart anything after every 2 days. Okay, and then cool pineapples. Things were fine. Our findings after oxidizing vehicle stream, they were super exciting. So the Rust endpoint was about 2 times faster than the JVM version, ignoring caching. Calls to the DB would take about 2 to 3 seconds. Rust calculates 700 updates every 100 milliseconds. Actually, initially I was a bit concerned because I was running in debug mode and it was running a bit slow. So I was like, well, it feels a bit slower than the JVM version. And then I forgot that I hadn't run cargo run release. I ran cargo run release in my laptop, just developing, and I think it took about 2 seconds or so. I was shocked, so I went back and then I had to just monitor it. And then lo and behold, I saw that MongoDB was actually taking most of the time. Once the data came back from MongoDB, and I could see it from the CPU switching from MongoDB to Rust, it would just happen instantly. So I had to like just simulate thousands. I think I did like, was it, I think 100,000 updates, just simulating them, just so I could see how long the Rust portion took. So I came about 100 milliseconds per 700 updates. And then where we used to calculate streams every 7 seconds, because JVM took 5 seconds per loop, we just run a loop every few seconds. We can now calculate updates every 4 seconds, but we don't do that because updates every 4 seconds means somebody receiving data every 4 seconds, and not much changes between 4 and 7 seconds. So it would just be a waste of somebody's data, especially when most people will be on mobile data. Cool. So the output, we freed 19 gigs of RAM. 19 freaking gigs. Okay, 2 of them would have been from moving from Apache Ignite to just a simple TTL. We will sometimes see a spike in our RAM. So we went from, we can actually run vehicle streams on a 1 gig container now with 2 cores. And I think that's what I haven't isolated it here actually. Where we used to use, in the past 162 days, well, since I last restarted the server, we've only used 80 hours of CPU. Previously, we would have used, I think at 160 days, we would have used maybe, I don't know, 20 to 30% of the time would have been dedicated to vehicle streams. And it's only 20 to 30% because obviously at night when there's no vehicles running, our services generally end at 9 p.m. Vehicle stream sort of just keeps quiet because there's nothing to calculate. Okay. Okay, so to recap, we didn't put everything to Rust as we would have wanted. It was hard to, we had to consider the cost in time spent and benefit being diminishing. The time spent being, the more I worked on it, the more sleepless nights I'd have, and the more weekends we'd have to stay home and not go out and do stuff. And then the benefits were, well, I've already saved 19 gigs of RAM. I can cut down from $170 per month to about $50 per month. The Rust ecosystem still lacks crates that would enable fully porting, so we use Firebase extensively, and there isn't, last time I checked at least like 4 or 5 months ago when I needed to do something with Firebase, there isn't really good support there. There's some people who are trying to, who are creating an HTTP interface, but you find that it's lacking in quite a lot of stuff that you want to do. And then geospatial libraries are time consuming to port, which was our main experience. So we just moved vehicle streams and other smaller services to Rust. I didn't mention some of them, but there's quite a lot of stuff now that just runs on Rust. It's like fire and forget, just restart it and then go away, come back after a few months when you need to change the code or whatever. We use nets.io and Node.js to handle streaming, which was hard in Rust. So I recommend using nets.io if you currently use Kafka just for streaming your data. Okay, so was it graceful? We managed to keep the surface unchanged while rearranging RPCs. Our users would have only noticed performance increase in the get trip update thing, where previously it would take about 2 seconds and now it almost loaded instantly. And then we actually found bugs in the JVM version while potting. Okay, so what if I can't put everything in terms of oxidizing? A lot of the talks in the past 2 days have been around using FFI, well, the CFFI interface, when you need to incrementally port your services. So what you can do is you can extract parts of your applications to Rust, like the talk from Develer was also like about that. So use FFI where feasible. If you haven't used FFI, Jake Golding, aka Sharpmaster, has a very interesting omnibus there. It just doesn't have Java, I think, but it's got quite a lot of the other languages. The interesting thing with FFI is that it's got a bit of overhead, but it's constant compared to going through the wire. So interestingly, at work we've started using Rust. It's a case of if management don't know what you're using, you can use whatever you want. So that's how we sort of Trojan horsing Rust into our workplace. We had a time value of money calculation that ran in about 600 milliseconds in Java. After the JVM starts optimizing it. We ported it to Rust. We found that it runs in about 100 milliseconds. But because of the amount of data that we move between Rust and Java, the overhead that FFI was creating was about 600 milliseconds. So the result was that we actually couldn't use it because it was slower in Rust because of the moving data around. Passing protobuf via FFI is pleasant. There was a hex.mozilla article recently about how they were using a Rust application in iOS and Java, in Android. You could also use gRPC or other typed RPCs. gRPC is more flexible than FFI because sometimes your applications don't live in the same machine, so you want to go through the wire, and instead of just sending JSON, the benefit of the gRPC is that you know that your data is well typed, so you avoid a lot of the errors that you normally get, although Serde handles that for us in the case of Rust. So just a quick detour, are we gRPC yet? Would anyone say yes in terms of us being gRPC in Rust, or no? Oh, probably a no. Okay, cool. So gRPC was the source of a lot of the pain that we had when we were porting from Rust. We cycled through 3 gRPC crates, as I've mentioned. We've grown with Tower gRPC from the days of that of that warning to 0.1 being released a few days ago. It's still not feature complete. Auth and interception are still very manual. TLS support is very difficult, but typically you hide it away from the end users. You just put Nginx as a proxy in between anyway. Okay, so next steps. Our initial port was about 10 to 7 months ago. Well, between 10 and 7 months ago. The ecosystem is improving. I've played a bit with more WASM, but if you look here at the screenshots, this is actually our website usage data. We still have a lot of people hanging on to Opera Mini. It's very painful for us because you try to implement something new and then you have to consider the Opera Mini people, etc. So effectively, we've got about 31% of our users supporting WebAssembly. I've tried using WebAssembly for the vehicle stuff to sort of make it to create an estimate between every 7 seconds to sort of create a smoothly moving vehicle in between. But it's no use putting it to prod because I'd have to worry about Opera Mini users, etc. So the other idea is to port all the other non-streaming RPCs to Rust. So we'll see as time goes along. Any questions?
And the question is not really Rust related, but you mentioned nuts.io for data streaming. Comparing it to Kafka, are you using the streaming service of nuts or just pure nuts?
No worries. I was using just the streaming service of nuts. So doing it, I would serialize protobuf into bytes, just send it to a nuts channel, and then subscribe on the other end, and then just deserialize the gRPC, the protobuf message into a JavaScript object. So just the streaming part.
Thank you for the interesting talk. Also, it sounds like a great project and great progress. So I'm curious. You mentioned you didn't want to spend time setting up Prometheus or Grafana or something like that. So how did you collect all the latency metrics? And also, what was the reasons you decided to not integrate Prometheus, for example? Like, are there any problems and so on?
Cool. Thank you for the compliment. I actually didn't mention an important detail. I use open tracing quite a lot with Jagger tracing. With Rust, it's very manual right now. There's a library called Rust Racing, I think. You have to implement the tracing methods, calls, etc. Within every function. So I use that to get not really latency, but to get spans of how long each part of the application runs. The reason why I haven't set up Grafana, etc., they're actually running on the server. So it's, I think GitLab runs its own instance, and then there's one in a container somewhere. It's a function of the time investment. So I understand how they work. If I needed to use them at work, I would be able to get it up and running. But for my case, I've got an external monitoring service that just pings the website, and then if the website is down, it lets me know. So from that perspective, putting them on there, I'll be getting statistics which I would rarely look at, and it just felt like a lot of time spent in not getting a lot of benefits from it. Not that the services are not beneficial, just that for me, because this is sort of a passive service, I wouldn't really come back and look at them much.
Any? We're set. Okay. Thank you again, Neville. Thank you very much.